examples on Euler's theorem. Verify Euler's theorem for the function u is this function, and second example u is this function. Obviously, these functions are homogeneous functions, both u in the first example and in the second example. So observe the degree of this homogeneous function. So u is this, u is a homogeneous function of degree. The degree of the numerator is 1 by 4 and the degree of denominator function is 1 by 5. And here the degree of this total function is degree of the above function minus degree of the lower function. Because if we find tx ty, if we replace x by tx, x by ty, then we have t raised to 1 by 4 divided by t raised to 1 by 5. And then t raised to 1 by 4 minus 1 by 5, that is 1 by 20 is its degree. So by using so if you consider this function, then the degree of this is a homogeneous function of degree 2, this is a homogeneous function of degree 1. If we replace x and y by tx and ty, then we have t square x square, t square y square. If we take t square common, then we have x square plus y square. And if we replace x and y by tx and ty, then we have t as a common in the denominator. And then t square by t is what? T raised to 1, that is 1 is the degree. So degree of this is 2, degree of this is 1, and so 2 minus 1 is 1. So if there is division, then the degree of the total whole function is the degree of numerator minus degree of the denominator. Okay. So 1 by 20, this subtraction is 1 by 20. So u is a homogeneous, this function, homogeneous function of degree 1 by 20. And therefore by Euler's theorem, x dabba u by dabba x, instead of we also use the notation f. So what is the Euler's theorem? X dabba f by dabba x. So in the Euler's theorem, the function is f or u. So x dabba f by dabba x plus y dabba f by dabba is nf. If we do not fxy as u, then we have the Euler's theorem x dabba u by dabba x plus y dabba u by dabba y is equal to nu. So what is n? N is the degree of that function. And so here the degree of the function is 1 by 20. And so by Euler's theorem, we have x dabba u by dabba x plus y dabba u by dabba y is equal to 1 by 20 u. So the notation for the function is u. If the notation is f, then write here dabba f by dabba x dabba f by dabba x is nu, nf. Okay. So here is the notation is u. So 1 by 20 u, nu. So this is by using Euler's theorem. So, and we'll find this LHS by using finding w by dabba x, that is partial derivative of this u with respect to x and y. So u is this function. So in order to find the partial derivative of this function, this simplification is necessary. That is, take log of both sides, then log a by log b is log a minus log b, and then differentiate with respect to x. Then log u, derivative 1 by u, dabba u by dabba x, and the log fx rule 1 by this quantity, this bracket, into the derivative of this bracket with respect to x is 1 by 4, x raised to 1 by 4 minus 1, that is minus 3 by 4, minus the same derivative of this factor is 1 by this factor, into derivative of this with respect to u is x is what? 1 by 5, x raised to 1 by 5 minus 1 is minus 4 by 5. So we have this answer, 1 by 4, 1 by u, x dabba u by dabba, that is multiplied by x, then 1 by 4, x raised to 3 by 4 minus 3 by 4, and x raised to 1 is minus 3 by 4 plus 1, that is 1 by 4. Similarly, x raised to minus 4 by 4, 4 by 5, and x raised to 1 is x raised to minus 4 by 5 plus 1 is 1 by 5. So base same, then addition of power. So we have this 1 by u x dabba u by multiplying. Then similarly differentiate this with respect to y. So we have this derivative y raised to 1 by 4, its derivative is 1 by 4, y raised to 1 by 4 minus 1, 1 by 4 minus 1. So 1 by 4 minus 1 is right here. Okay, directly using this second, we have this. That is the same procedure, differentiate partially with respect to y and then multiply by y, we have this. Okay. And then addition of these 2 and 3 is 1 by u, take u 1 by u as common, x dabba u by dabba x plus y dabba u by dabba y in bracket. So 1 by 4, this base is same, so addition is what? 1 by 4 is common factor, x raised to 1 by 4 plus y raised to 1 by 4, and take 1 by 5 as common. So and negative sign as common. So we have x raised to 5 base same y plus y raised to 1 by 5. And then this is 1 and this is 1. So 1 by 4 minus 1 by 5 is 1 by 20. And then shift this u 1 by u to RHS. So we have 1 into u. And that is we have to prove. So here the Euler's theorem is verified. That is, this answer is by Euler's theorem, and this answer is by using actual calculation, by taking partial derivative with respect to x and y, and then find the value of LHS. We have the same answer. Similar problem, that is, we have to verify the Euler's theorem. So x w by x plus y w by y is what? This is the homogeneous function of degree 2, numerator degree is 2, denominator is 1, 2 minus 1, that is 1. So 1 u, that is u. So this is by using Euler's theorem. Then actually we define, we find w by x and w by y. So for in purpose of the partial derivative, take log of both sides. So instead of this taking derivative with respect to x and y directly of this u, we take the log of both sides and then find derivative. That is, we have this answer 1 by this x square plus y square into derivative of x square plus y square is 2x, 1 by x minus y. This is, and then multiply by x. So x into x square, here is x. Similarly, we have with respect to y derivative, and then multiply by y. And taking addition of 2 and 3, we have this answer. Okay, so that is 2 plus this is x minus y and divided by y minus x by y, y minus x. If you take minus sign common, then x by x minus y, here is minus sign. So we have the answer minus 1. So his answer is plus 1. That is, and then u shift the u. So we observe if this and up the above is this answer, this equation by using Euler's theorem, both are same. Therefore, Euler's theorem is verified. So if this, then show that this. Okay. So here we use only one procedure. That is, we use the Euler's theorem. So u is sine inverse this. So shift this sine inverse to LHS. So sine u is x plus y divided by root x plus root y. And this RHS is the homogeneous function of degree. Degree of numerator is 1, degree of denominator is half. So 1 minus half is half. So this whole function on RHS is a homogeneous function of degree 1 half. And so by using Euler's theorem, suppose this function is denoted by suppose notation small f, then by Euler's theorem, x dabba x dabba by dabba x, that is f means sine u, plus y dabba y of sine u, that is sine u. This function becomes a homogeneous function of degree 1 half, and therefore by using the Euler's theorem, x dabba x of this sine u plus y dabba y of sine u is equal to 1 half sine u. That is x dabba by dabba x plus y dabba by dabba y is equal to nf. F function is what? Sine u. Sine u is this function, and this function sine u is what? Is a homogeneous function of degree half, and therefore by using Euler's theorem we have this. So dabba x of sine u by chain rule, dabba u of sine u into dabba u by dabba x, dabba y dabba u sine u dabba u by dabba y, this function. And then derivative of sine u is cos u. Sine u is cos u, and then dividing by cos u throughout, we have x dabba u by dabba x plus y dabba u dabba y, 1 half sine u by cos u is tan u. That is, and that is we have to prove. The next example is u is tan inverse x cube plus y cube divided by x minus y. Okay, and then show that this x dabba u by dabba x plus y dabba u by dabba x sine u, sine 2u, and this is we have to prove. So use the same line of proof that is used in Euler's theorem and corollary in the Euler's theorem. So what is the procedure? So this tan inverse u to LHS, what do we have? Tan u is x cube plus y cube divided by x minus y. And suppose this function is z. We denote this function by z, that is tan u or x cube plus y cube. And then this z becomes a homogeneous function of degree 3. The degree of numerator is 3, degree of denominator is 1. So 3 minus 1, that is equal to 2. And therefore by Euler's theorem, x dabba z by dabba x plus y dabba z by dabba y is 2z. Use the notation z or f. If you use the notation f, then what do we have? X dabba by dabba x plus y dabba by dabba y is equal to nf. So use the notation Z or phi or psi or small f or capital F. Okay. So here is the notation is Z. So by Euler's theorem, x dabba z by dabba x plus y dabba z by y is 2z. In this example, we also use the notation for sin u or this function as a z, and then write x dabba z by dabba x plus y dabba z by dabba y is equal to en z. Okay, en, and then write z as sin u. Here is also the substitute z as tan u. So use the notation or directly write this tan u is the homogeneous function of degree 2, and then write this step that x dabba x of tan u plus y dabba y of tan u. Z is tan u. Okay. And then use chain rule. X of tan u is u of tan u into w by x, and y of tan u is what? U of tan u into u by y. And then derivative of tan u with respect to u is sec square u. Then sec square u. Then dividing throughout by sec square u. So we have 2 tan u by sec square u. Tan u means sin u by cos u. Divided by sec square u means into cos u. Then we have cos 2 sin u cos u, and then that is sin 2u. That is we have to prove sin 2u. Then we have to prove this. Okay. So differentiate one with partially with respect to x and y, and multiplying by x and y, and then add 2 and 3. So the same procedure that is used in the corollary of the Euler's theorem. So differentiate this equation 1 partially with respect to x. So x dabba square u by dabba x square plus dabba u by dabba x into x derivative of x is 1. So u into v rule. Plus y is constant, derivative of dabba u by dabba y with respect to x is dabba square u by dabba x dabba y is equal to sin 2u, derivative is cos 2u into 2 derivative of 2u into dabba u by dabba x. Because this sin 2u is the function of u, and we have to differentiate with respect to x. So dabba x of sin 2 is what? Dabba u of sin 2 into dabba u by dabba x. So multiply by dabba u by dabba x. And then shift this dabba u by dabba x to RHS and take this dabba u by dabba x as common. So we have 2 cos 2u minus 1 in bracket. And then multiplying by x. So we have x square in here xy, and here is the x dabba u by dabba x. This second. Similarly, differentiate one partially with respect to y. We have this x is constant, and then derivative of dabba u by dabba x with respect to y is dabba square u by dabba y dabba x plus u into v rule y dabba square u by dabba y square plus dabba u by dabba y, derivative of y is 1, is equal to the derivative of this sin 2u. Sin 2 is what? Cos 2u into 2 into dabba u by dabba y. Okay. 2u, derivative of 2u is 2, and into dabba u by dabba y, because derivative is with respect to y. And this sin 2u is the function of u. So use chain rule. And then we have this, shift this dabba u by dabba y on RHS and take dabba u by dabba y common, and then multiply by y. We have this. Then adding 2 and 3, we have x square dabba square u by dabba x square, and this xy into dabba square u by dabba x dabba y, and this xy into dabba square u by dabba y dabba x. The addition is what? 2 times xy dabba square u by dabba x dabba y. Because this function is polynomial function, and polynomial function is always continuous everywhere. So these two are same, dabba square u by dabba x dabba y and dabba square u by dabba y dabba x, both are same. It's become 2 times plus dabba square y square dabba square u by dabba y square is equal to the addition of RHS. Then take this 2 cos 2u minus 1 as common factor. We have in bracket x dabba u by dabba x plus y dabba u by dabba y. And by using equation number 1, x dabba u by dabba x plus y dabba u by dabba y is sin 2u. Substitute that value of this bracket as sin 2u from equation number 1. And then calculation of this is what? Cos 2u. There are 4 values of cos 2. Out of that, substitute 1 minus 2 sin square u. Cos 2 theta is cos square theta minus sin square theta, or 1 minus 2 sin square theta. So cos 2 theta is 1 minus 2 sin square theta. So cos 2 is 1 minus 2 sin square u into sin 2u. And then the calculation of this is what? 1 minus 4 sin square u. That is, we have to prove this second equation number 2, sin 2u in one bracket, 1 minus 4 sin square. So the same problem, second problem, next problem, u is x sin inverse y by x. Show that this. So u is equal to x sin inverse y by x. This is the, if you consider f of tx ty, if you denote this function by fxy, then if you consider f of tx ty, then substitute x and y as a tx and ty. So tx sin inverse ty by tx, and then t get cancelled. So we have t in bracket x sin inverse y by x, and x sin inverse y by x is f of xy. So f of tx ty is t f of xy, And so this u or f is the function, homogeneous function of degree 1, because t raised to 1. And then by Euler's theorem, we corollary of Euler's theorem. What is the corollary of Euler's theorem? X square dabba square u by dabba x square plus 2xy dabba square u by dabba x dabba y plus y square dabba square u by dabba y square. Here is the notation f. U. So write u, notation u instead of f in corollary of the Euler's theorem. N minus 1 into u. Okay, so n is 1 and 1 minus 1, n is 0. So we have the answer 0. Okay, so we have this by using corollary of Euler's theorem. So these are also, this is the problem. U is sine inverse root x plus root y. Show that this. Okay, so u is this. So root x plus root y is sine inverse u. Suppose z. And then root x plus root y is the homogeneous function of degree half. Okay, homogeneous function of degree half. So noted of this calculation, directly we consider that if we write x by tx and y by tx, then we have t raised to half as a common factor. So root x plus root y, that is z, is the, that is sine inverse u, or z, or this root x plus root y is the homogeneous function of degree 1/2. And then by Euler's theorem, x dabba z by dabba x plus y dabba z by dabba x, this is the notation for this function, root x plus root y, or sine inverse u is denoted by z. So it is a homogeneous function of degree half. Therefore, by Euler's theorem, x dabba z by dabba x plus y dabba z by dabba x is nz, that is f 1/2 z. And then substitute z as sine inverse u. There are two values. This value is useful to determine the degree of the function, and this is useful in the next proof, that is substitute z as sine inverse u, and here z as root x plus root y z. Okay, and then because observe what is to prove, and then substitute z in this place as a sine inverse u, and in this place as a root x plus root y. Then dabba dabba x of sine inverse u, use dabba chain rule, dabba dabba u sine inverse u into dabba u by dabba x. Similarly, here is dabba u by dabba y. And then derivative of sine inverse u is 1 by root 1 minus u square. Similarly here. And then multiply by root 1 minus u square. So we have this step. And then x dabba u by dabba x plus y dabba u by dabba x is 1/2 root x. Then 1 minus u square. U is sine, u is what? U is sine root x plus root y, it's square. Sine square root x plus root y. And in 1 minus sine square is cos square, and its root is cos. So cos root x plus root y, that is we have to prove this. Okay. So u is sine inverse x by y and plus y, tan inverse y by x. Then show that x dabba u by dabba x plus y dabba u by dabba is good. Say here, if you do not, this is u, then this is the homogeneous function of degree 0. That is, if you find, if you replace x and y by tx and ty, then what do we have? Sin tx by ty is sin x by y plus sin inverse, tan inverse, sin inverse. Tan inverse ty by tx, dt get cancelled. And we have the same answer, that is t raised to 0 into this u f of xy. So f of tx ty express it as a t raised to 0 f of xy. Therefore, this is a homogeneous function of degree 0. And therefore, by Euler's theorem, x dabba u by dabba x plus y dabba u by dabba y is nu. What n is 0, so 0 u is, that is 0. So these are some problems for exercise. Solve all these problems by Euler's theorem or Euler's corollary. Okay, so these are another some solve examples of Euler's theorem, related to Euler's theorem. We will see in the next lecture.